and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In the previous module we looked at Maxwell's equations. Well, we looked at all other equations except for Maxwell's contribution, namely the displacement current. In this module we will talk first briefly about the displacement current and then complete the Maxwell's equations and then talk about the boundary conditions in this as well as in the next module. Now here is a set of equations which whose history we have studied in the previous module. We recognize that the first equation is Faraday's law because it relates the flux linkage to a particular circuit to the EMF that is generated in that particular conductive circuit. These two equations are Gauss's law, one for electric field which says that the source for the electric flux density vector D is the charge density in that particular region, okay, and it also shows Gauss's law for magnetic case shows that there is no source for the B field. In other words, there are no isolated positive and negative magnetic poles and therefore del dot B is always equal to 0. This law which I have saved for the final one to discuss is the Ampere's law. We have already looked at Ampere's law in the context that if you have a current carrying wire, then there will be a magnetic field around it, and if you then take any closed curve, okay, and then integrate the magnetic field around that particular curve, then you will obtain quantity called as magnetomotive force, and the source for this magnetomotive force will be the current that is propagating. Okay. So suppose this is my wire which is carrying a certain current I, and then the magnetic fields will be surrounding this particular current. They will be in the form of circles with decreasing amplitude as you go away from the current carrying wire. And if you take any path, okay, so for example if I take this particular path and then integrate the magnetic field, then I obtain what is called as a magnetomotive force, and this magnetomotive force, the source of this magnetomotive force must be the current that is coming out of this patch of area. So there is a patch of area here, okay, the open surface. So whatever the current that would be flowing through this one will constitute the source for the magnetomotive force. In this particular problem, this path which I have taken shown in the red curve does not enclose any current because the current is directed along this blue line, and therefore the magnetomotive force for this case will be equal to 0. On the other hand, if I take this particular curve, maybe a circle around this one, then I know that if I integrate the magnetic field around this constant radius circle which is shown in this orange color, then it will enclose a current because the current is coming right perpendicular to that through that particular circle, and therefore the source for this magnetomotive force will be equal to the current that is being carried by the filament. So far so good. So this is what Ampere had in mind, but then there is a inconsistency between the equations that we have written here. So before Maxwell, when you put together all the equations, along with that there is a current continuity or the charge conservation equation. The charge conservation equation that we have discussed, in that any closed surface, if you take any closed surface S0, if you take and then find out what is the source for this J, that is if you find that there are these current density vectors coming out of this closed surface, then the only way that can happen is when the charge density here inside is decreasing with respect to time. Okay. So assuming that these charges are all positive charges, if the amount of positive charge decreases, then it constitutes a conduction current J. So this is what people kind of understood before Maxwell, but unfortunately if you look at these equations, there is some inconsistency in the equation. What is that inconsistency? Let us take this Ampere's law, okay, and then dot on both sides with del, okay, operator. So we actually calculate del dot del cross H. So you have to dot on both sides, and clearly the left hand quantity you can show by actually writing out in various coordinate systems that this left hand side quantity will always be equal to 0. Even when H field is dependent on time, this quantity will always be equal to 0. This seems to indicate that if I take the divergence of J, that should be equal to 0. But unfortunately this is not consistent with the charge conservation. Either we let loose of the charge conservation, that is either we let go of the charge conservation and then accept the fact that del dot J is equal to 0, but if we do that, then you can create charges whenever you want and you can destroy charges whenever you want. You can kind of remove this conservation principle at all. You can continue to create charges and you can create an infinite amount of charge. Clearly such a thing does not happen in nature. So conservation principle is more important because it has been observed that no matter what you try, you cannot create charges, okay, and have no current flowing through it. So the charge conservation is a deeper principle of physics experimentally, and therefore that cannot be violated, which only means that the conclusion that we obtain from Ampere's law must be wrong. How do we fix this? Well, in order to fix this, we simply use the equation that we have with the charge conservation. What we do here is that we replace rho v by del dot d as in from the Gauss's law, and then rewrite this equation. So what we obtain, from this equation is that if I take del dot j, then del dot j must be equal to minus del by del t del dot d, and interchanging the operations of time and space variables. So you get minus del dot del d by del t. Now I can bring this quantity on the right hand side, this divergence of del d by del t onto the left hand side, and then essentially obtain a simplified equation which tells you that del dot j plus del d by del t is equal to 0. Okay. Now this equation kind of makes sense, or this is called as the current continuity equation. Okay. Why it is called current continuity equation? Because if you go back to the original expression for what is the divergence of a given vector field, you would see that it has to do with the closed surface over which you are evaluating that particular vector quantity. In this case it would be j plus del d dot ds, and divided by a unit volume in the limit of volume going towards to 0. So you can split this again into two integrals. So you will have j dot ds divided by delta v in the limit of the volume delta v going to 0. This of course is the restatement or rewriting this del dot j itself, right, and this would be equal to minus again in the limit of the volume going to 0, you have del d by del t. So if I interchange the operations of del by del t and the space operation, so I first evaluate this d dot ds over the closed surface that I am evaluating, and then take the time derivative of this, okay, divided by delta v. Now what is the on the closed surface, if you evaluate the electric flux density, what quantity do you obtain? This quantity that you evaluate is simply the electric flux density. So what you have is that del dot j is actually equal to minus del electric flux density by del t. So this electric flux density change, or the change of the electric flux, not the flux density, electric flux itself gives you the displacement current, because electric flux is related to d. It was called earlier as the displacement vector. We now call it as the electric flux density vector, but earlier it was called as the displacement vector, and therefore the time rate of change of the displacement is equal to the displacement current, and this equation is called as the current continuity equation. Okay. So this is a simpler thing that you need to understand out here. These are exactly not del psi e, but psi e is actually this quantity integral of d dot ds, but you get the idea, right. So here you have completely a conductive current, or the current because of the motion of the charges in wires or in other conductive planes, for example, whereas on the right hand side you have a quantity that is not really dependent on the conductivity, right. So this quantity can actually exist even in free space, and in fact such a current would actually exist between the two plates of a capacitor, as we will discuss very shortly from now. There is only one small point that we need to note at this stage of our development of displacement current density, is that whatever we did from the previous calculation showing that del dot del cross h equal to del dot j, and then subsequently defining the displacement current as del d by del t, did not really happen this way, because Maxwell did not know what vector analysis meant. Vector analysis was invented after Maxwell died, and therefore he did not follow this path at all. Rather than tracing what Maxwell did or what path he did, because that is too complicated for this course, we will assume that this law, which does not contradict with any other previous laws and is consistent with conservation, charge conservation principle, is that we take this displacement current as another type of a current, okay, and we simply try to show where this displacement current might originate, okay. In order to do that one, let us go back to this simple experiment that you can think of. Let us say we have a certain current source, okay. What is the objective of a current source? It has to supply a certain current. Let us call this current as some I0, and the current, let us say, is flowing through this thin filament of wire, and then it comes back to the current source itself. So, there is actually a continuous current flow, which as it should be, because the current cannot be in this way. So, current has to flow in a complete circle. So, this is the current that is flowing. Now, you imagine that I actually take a curve, okay, does not matter which way I take a curve. So, since the current is directed along this one, so I will take the curve in this particular way, okay, just to be consistent with what is called as the right hand rule. So, I take this particular current, and then now this is the contour which I take, okay. Now, you know that if I take this contour and evaluate the magnetic field around this contour, I will be generating the magnetomotive force, and that magnetomotive force will be equal to whatever the current that would be contained by this patch of area, right. So, by this patch of area, because there is a current coming out, right. So, there is a current coming out, and since you are considering only the open surface S here, let us call this as S1, because we are going to soon write another surface here. So, the current through the surface S1 will be equal to I0, okay, because that is the current that is being passed through that, and this will act as the source of the magnetomotive force over the contour C, okay. So, just to refresh your memory, the magnetomotive force MMF over this contour is simply the integral of H over that particular closed curve that we have considered, okay. So, so far no problem. And how did we calculate the current through the surface S1, which is the current density through ds, and if you just kind of not worry too much about the problem that the current density kind of seems to be infinite because the current is filamentary, but just remember that the total current out of any surface that you are considering, the open surface, that is important, the open surface whose contour is the same as C, that current is exactly equal to I0. The source of the MMF will be equal to the current as it should be. So, so far no problem, right. Now, there is also no problem if you were to consider a different kind of a surface. So, let us imagine that I actually have some sort of a balloon out there, okay, and this balloon is the surface that I am considering, okay, and so now what is the surface I am considering? So, this was my contour, okay, so some direction C, and the balloon that I consider will have the same contour, okay, and it will go through like this. You can think of this as a sack of or a bag or a sack. This is the surface S2, let us call this, okay, and this portion that I have shown here, where my pen is going around, this top portion is actually left empty. So, you might imagine that this is a surface that I am considering. So, you can imagine that this is the contour C that we have considered, okay. If I now take a paper and then just tape the paper on top of it, okay, and then just look at what the marks that the paper does, and imagine that this part is not actually existing, okay. If I remove this part, it is not existing, then you actually have a open surface whose contour is this one, and if I now pierce that paper through this pen, then there will be a current going into it, right. And because this current continues and comes out of this open surface, you have to imagine a paper being wrapped around this, and then this current going in and then coming right out of the paper, okay, and that would be the current that you have. Instead of doing that, you can consider this as your open surface. You can observe here that the contour is now left open, and whatever this surface that I have drawn, so this edge combined with this closed path over here, so this surface is the one that is now, so this entire thing is now the surface, okay. The paper has been removed and you just have an empty kind of a emptiness inside here. So, there is a small hole inside, and you can have a current going through, and because there is a current coming out, this current would come out, okay. Again, this current is a filament, and it does not matter whether I consider this type of a curve or put a paper and then consider just the current going through that paper. Both curves essentially give me the same amount of current, which will be equal to the MMF of that particular contour. So, this is the MMF of the contour, okay. Now, so far that is all right, huh? So, if I use surface S1 or I use surface S2, I essentially obtain the same current, and same current means that the value of the MMF is unambiguous. There is no doubt about what MMF I obtain, that MMF will be the same. The MMF will be in fact equal to I0, okay, whether I evaluate it over surface S1 or evaluate over the open surface S2. So far so good. Okay. Now let us see what happens. Now what I do is I take the same scenario, okay, I have a current source and then I pass through this and somehow ground here, okay. So somehow I ground here, there is nothing coming out of this, okay. So there is clearly a discontinuity, or if you are not too happy with this one, let us keep the current flowing completely, but then put up a capacitor, okay. So we assume for now, we will talk more about capacitance in the coming modules, that this capacitor is filled with a material which is perfect insulator, okay. That means there are no free currents or free charges anywhere to be found in this particular region. Now the current I0 is coming through, current I0 is coming through this current, and obviously because the total current in the loop is I0, from your normal circuit theory you simply expect that this current has to go, you know, and out of this plate and then essentially has to pass through the current source and then come back. Only catch is that now the MMF seem to become, you know, ambiguous. Watch what happens. Let us initially consider the same, you know, loop, okay. So since the current is coming out in this particular way, I will orient my contour along this way. So this is the contour. So there is no problem with the MMF. The MMF is equal to I0 because I0 is entering and I0 is leaving. So and if you integrate the magnetic field around this blue curve, you essentially obtain the magnetomotive force. Now as before, we consider first one surface S1, okay, which is given by this hatched area. So going back to our example, so we will come back to that one, the visual way of thinking of this one. So over this open surface S1, the current, you know, passing through this open surface is equal to I0, and therefore the magnetomotive force U because of this contour C and the open surface S1 also seems to be equal to I0. So far there is no problem. Now what we do is we again consider this balloon kind of a surface, and we consider the surface to be something like this, okay. So this is my balloon surface that I have considered. So please again understand that this hatched area has been removed. So let me try and remove the hatched area for you, okay. Oh, in the process I actually also removed something else, okay. Let me retrace this. So I have a curve C here, okay, and then I have this balloon which is passing through the plates in between, okay, passing through the plates in between, and this is oriented in this particular way. So let us call this as S2. So you can imagine that this sac which we have drawn here has been, you know, put over this wire. Please note that the line that I have shown here, the black line, is actually going through this. It is not touching, or it is not, there is no area to touch for this, okay. The current would simply come here, in between go through, and it will only touch the bottom plate over here. So only at this point the current should touch. But unfortunately we have just seen that the current, there is no current coming out of this point, right. So it's like this, imagine this, okay. So you have this current contour, okay. So this is the sac that I am considering. So now imagine that current is going in, okay. So you can imagine that the current is going in, but it kind of stops in between because I have put up a plate here, okay. So you have to imagine that I have taken this contour and then I have stretched this open surface into that, and my current is going here and is getting stopped because it encounters a nice perfectly conducting plate, okay. So there is a space between what this plate encounters, or rather the plate and the hole inside here. So there is no current. So this tip is not touching the bottom part, or essentially not touching this and then coming out. So in that case, what would be the current enclosed? Clearly the current that must be enclosed, there is no current enclosed here, no current, no current, no current, no current, no current, no current. The only current that should have enclosed is via this way, but there is no current line out there, there is no wire out there, and therefore there is no current coming out of this surface. So what it indicates is that the magnetomotive force associated with this contour, when you consider the surface S2, must be equal to 0. Now clearly something is wrong, because just by changing the surfaces, whether it is the red surface which is the open surface or another surface S2 which is again open, but it gives you a different answer, you might seem to obtain two different answers. So, the case when current seems to be discontinuous is that the corresponding magnetomotive force seems to be dependent on what type of a surface you consider in order to evaluate the magnetomotive force, clearly something that is not to be having, right. So, you cannot have your answers dependent on whether on Monday you woke up and decided to take S1 and on Wednesday you woke up and decided to take S2. So, you cannot have such ambiguous values for the magnetomotive force, and therefore, this is kind of indicating the failure of Ampere's law. To bring about more clearly what is happening, we now let us close this surface. So, we actually instead of leaving it open, we close it, we pinch the surface, essentially obtaining something like this. So, we pinch and then the surface S2 becomes closed. Okay. So, here we go back and then make that one. So, the surface S2 is essentially closing. So, let me try and see if I can remove this one. So, let me let the current go back here, and now I draw the closed surface, right. So, this is the closed surface that I am considering, and what is happening to this closed surface S2, there is some current I0 entering, but there is nothing coming out of it. Or is there something coming out of it? Yes, there is something coming out of it, because this filament lands on this plate. This plate is a perfectly conducting plate. Okay. What it means is that if current I0 is coming through here and lands on this perfectly conducting plate, there will be charges induced on this plate, and the amount of charge will keep on increasing. So, the charge has nowhere to go, but kind of piles up at the surface. Okay. The rate at which the current comes in will be the rate at which the charge is getting piled up, because you can write down the charge conservation equation for a closed surface that would look like this, or the closed surface S2, and then you would see that this current I0 entering, okay, will give rise to the piling up of the charges. The density of the charges increases because of the current coming in. But these charges which have been piling up on this perfectly conducting plate has nowhere to go, because the only other conducting surface happens to be here. So, this is the second plate of the capacitor, and here there is nothing out there, right. So, there are no or nothing is happening. But if you remember from your electrostatics, now although the case here is not strictly electrostatics, if you remember the ideas from electrostatics is that if there are charges here, there will be equal charges piled up on the other side of the capacitive plate. Okay. And between these two charges there will be E field, and E field will lead to D field, and rate of change of D field, because the rate at which charges are getting piled is changing, therefore E is changing with time, D is changing with time, and this del D by del T will be changing with time, and it will take over when the conduction current ends. So, on this conducting plate, until this filamentary current, this is all conduction current, okay, which you can describe by the conduction current density J. If you are not happy with the filament of the current, you can imagine that there is actually a small tube of the current, okay, and then this tube will have a certain conduction current density. But once the medium is perfectly insulating or perfectly dielectric medium, dielectric is another name for an insulator, then there is no hope of finding a J vector here. You can't find a J vector simply because this medium is not a dielectric medium. So, the conduction current has to vanish. What instead happens is that this region will generate the D field, okay, and D field would look like this, okay, because the charges are all coming out. I am not assuming that there is another plate here, okay. I have moved that plate very far away out to some other region. So, these are these D fields, and when you now take a closed surface in this manner, entering to the top of this surface will be the conduction current, but leaving this surface will be the displacement current, okay, and this displacement current is given by del D by del T, and this must be equal to whatever the current that you are going to see over that particular closed surface. Okay. There is a minus sign out there because one is entering, the other one is leaving. So, you take leaving as a positive and entering as a negative, and what you obtain is the current continuity equation. Okay. So, this completes our introduction to Maxwell's equation. So, we can go back now with the fact that we have discovered, or we have kind of come up with a consistent way of writing down all the equations that agrees with all the experiments. Of course, it is not that we came out of all this, it was Maxwell who introduced this displacement current, and the importance of displacement current is this. In vacuum, right, so there is no way of having free charges or free currents, so there is no conduction current, there are no wires in the vacuum, yet electromagnetic waves travel, these electromagnetic waves carry energy, and for the waves to actually happen, you need a phenomenon in which electric field is changing magnetic field and magnetic field is changing in terms the electric field, and that link between the two is via the displacement current. Any time you have a perfectly insulating medium, you will have only displacement current. Anytime you have a perfectly conducting medium, you will have only conduction current, and if the medium happens to have both conduction and kind of a dielectric, that is, it is not a perfectly conducting material nor it is a perfectly insulating material, then you will always find a combination of conduction as well as the displacement current in such a way that the conduction current density entering through a closed surface will be equal to the, or the conduction current entering through a closed surface will be equal to the displacement current leaving that particular closed surface. Okay. So, we now gather all Maxwell's equation in one place, write down the corresponding constitutive relationships, and from then we look at what how these fields interact when the medium properties change. Okay. So, we begin with Faraday's law, we have already seen that one. So, Faraday tells us that curl in the point form, curl of electric field is given by the magnetic field change with respect to time. Similarly, curl of magnetic field H, right, this is given by, this is what we call as the Ampere-Maxwell law, because Maxwell contributed the displacement current. This would be given by the conduction current density J plus the displacement current density del D by del T, so that when you take del dot del cross H, there is no problem with this. Then there are two Gauss's laws, one for electric field and one for magnetic field. So, what are those laws? So, Gauss's laws are del dot B equal to 0, del dot D equal to rho V, and this B field is related to H field by this quantity. Mu 0 is the permeability of free space, mu r is the permeability of the medium. We will assume, unless specified, we assume that mu r is equal to 1 in our course. We have D, the electric flux density, being given by epsilon 0 epsilon r times E for the simple case that we are considering. Epsilon r is called as the relative permittivity, epsilon 0 is the free space permittivity. Okay. Add to this the current density vector del dot J equal to minus del rho by del T, del rho V by del T, and then we have Maxwell's equations, the constitution relationships or constitutive relationships, and the conservation equation, and we are good to go to study how these fields would be behaving in region 1 when material properties are different, and in region 2 when material properties are different, and what really happens on this boundary. Okay. In order to do that, we need to study boundary conditions, which is the subject of the next module. Thank you very much.